This is the exam 2 review on spectroscopy for the fall 2023 Organic 1 cohort. So of the 30 questions, the correct response is written in green under the question number. So there are 6 different sections here. Each has 5 questions. As we see with questions 1 through 4, they can have the A, B, C, and D responses are all for those questions. And then as question 5 has its own set of responses. So what we'll do is we'll go through and talk about the logic required to solve each question. So the screencast will take 30-45 minutes or so, but you can fast forward and just see the answers if you want. So we'll change the color here to red, do some marking up to understand the logic required for each question. What instrumental technique will inform of the presence of an odd number of nitrogen atoms? That is mass spec. So the odd N rule. So if there's one nitrogen atom in the molecular formula, that's going to give you an odd mass. So if you have an even number of nitrogens, that's going to give you an even mass. But typically, we're looking for that odd mass to inform us of an odd number of nitrogens. What instrumental technique will inform the presence of a carbonyl group? That's IR. So a carbonyl group is your carbon doubly bonded to an oxygen, and so that region is typically 1800 to 1650 reciprocal centimeters, depending on which functional group you're dealing with. What instrumental technique will inform of the unique type of carbon atoms? That's C13 NMR. And so again, that has the x-axis in parts per million from 200 to 0 ppm. That's where you'll see all the different functional groups, really separated by hybridization of the carbon, sp3, sp2, sp, and then finally which instrumental technique informs about the unique type of hydrogen atoms and their ratios. That's 1H NMR. And so we've been representing that as unique sets. So whatever number and then, their ratios. So for example, this would be 3 unique sets in their ratios here, 1, 2, and 3, whatever those numbers are. The sum of those numbers must be the total number of H's in the molecule. So moving on to question 5, what molecular formula matches this data? So the first thing we have is IR at 1800 reciprocal centimeters. And typically at 1800 is your acid chloride of the carbonyl containing functional groups. And then if you look at that fragment, what is that equal to? That's ClO. So you have those elements in that fragment. Mass spec, we have 2 masses shown at 106. That's the parent. Then 108 is the parent plus 2. So M plus 2 equals 108. And if you look at those ratios, it says 100%, 32%. And again, that's informing you that a chlorine is present in that 3-to-1 ratio. And we already saw that from the IR, so we're just confirming it with the mass spec. We'll come back to the mass spec in a second, but let's go and look at the 1H NMR. We see there's 1, 2. So 2 unique sets. Carbon 13, we have 1, 2, 3 unique carbons. and we already saw one of them in the IR data. So really, based on that information, we can take that existing fragment, the acid chloride, we can add 2 more carbons to it. And so that's going to give us right there 3 unique sets, but what we're not sure of yet is, does that jive with the mass of 106 and the unique sets that we see for the proton? And we can see that it doesn't, because we have this septet and this doublet signature in the proton. So if we look at what we've drawn so far, we have a CH2, a CH3. If we do the n+1 rule, this is going to be a triplet, that's going to be a quartet, so that doesn't match. So really what we have to do is insert another carbon on here. A septet is a signal with 7 lines. A doublet is a signal with 2 lines, and so what that is informing us is of the neighbors. So if we do n-1, that has to have 6 neighbors. This has to have 1 neighbor. And so if we have to add another carbon, we can do that one of 2 ways. If we add it here, we can see that that's not going to give us what we want, because now we're going to have a triplet, and then we have 3 plus 2 is 5 plus 1, that would give 6. So a line with a signal with 6 lines, and that's not what the data is telling us. So we're not going to go with that claim. We're going to put the last carbon here. And so that's going to introduce symmetry into the molecule, in which we have now the signal here with 6 neighbors plus 1, that gives you your septet. These 2 are the same, so they have 1 neighbor, that's going to give you your doublet. But let's go ahead and go back to this mass of 106 so that we can prove to ourselves there actually is 3 more carbons. So we can take 106, we can subtract out chlorine 35. That's the lower atomic mass isotope that's present in the 106. So if we subtract that out, we get 1. So we're going to get 71 here. And so we know that that chlorine is there from the different pieces of data. We know that there's an oxygen present, so 16. So we do this subtraction, 71 minus 16, so 11 minus 6, that gets us our 5. Whoops. We reduce that down, 6 minus 1, that gets us 55. And so 55 divided by 12, that's going to give us 4. So that would be 4 carbons, and then 55 minus 48, that would be the mass of all the carbon contributions, is going to give us 7 hydrogens. And that's what we see. We have 3, 6, 7 hydrogens. So this all jives to give us A as the response, C4H7ClO. We can eliminate bromine by MS data, because that would be a 1-to-1 ratio of the parent to the parent plus 2. We can eliminate nitrogen because of the mass spec data, so odd mass. We do not see that. So really you're between A and C, and then you just have to use the math of the mass spec to determine the ratio of C to H. in this next run of 5 questions, you're given a snippet of IR data, and you're asked to determine the functional group that's responsible for that. So in question 6, we have this broad peak that's spanning, quite a large wave number region, and we know that that's due to OH stretching, so it has that nice smooth peak, and then it goes up, and then you have this separation here between the OH and the sp3 hybridized carbon H stretching that comes next. 7, you have this gradual sort of broad signal that's merging into the CsP3 H stretching, so that's OH of an acid, so CO2H. Question 8, you have this nice sharp singlet, to the left of the normal sp3 hybridized carbon H stretching, so this is going to be an alkyne terminal CH stretch, so terminal alkyne CH stretch. Moving on to question 9, you have what looks like sort of an alcohol carboxylic acid mix, but you have these little blips down here, and so that's what's important. This ends up being the primary amine NH stretching. So these two little blips, even though it's subtle, those look different from the smoothness of the alcohol. Moving on to 10, what data matches this structure? So let's just go ahead and convert that to the MF. And we see that we have 1, 2, 3, 4 carbons. We count the hydrogens. 2, 4, 5, 6, 7. We have a nitrogen. So the nitrogen means odd parent in the mass. So let's see if we can eliminate anything. It looks like we can. We can eliminate C and D because of those even masses. For the parent, that leaves us with 69 is the parent ion. Now the CN, what does that mean? CN, if you draw out that Lewis structure, that's a nitrile. I think I added 1 too many carbons there. Let me just erase this last one. So triple bond, that's in region 2, so 2200. Both have that, A and B, so we can't eliminate anything just yet. What about, let's just go to the C13 data. We should have 4 unique carbons. They each have 4, but then looking at them, there's this difference here, 90 and 119. So maybe that's not too clear to us yet, which one is the real sp hybridized carbon. All the other values are the same, so we can't eliminate anything there. Let's go to the proton now. We see they're all the same chemical shifts, 2.33, 1.71, 1.71, 0.94, 0.94. But what differs, it looks like the 2.33 doublet versus triplet. So which one of those is real? And 2.33, again, that's moving farthest away from 0. So that has to be the thing closest to the carbon that's bearing the nitrile. So this is sp2, sp3, sp3, sp3. So this one needs to be closest to 0, and then you're moving, further to the left because you're looking at the influence of that nitrile group on the chain. So when we consider this carbon, there's 2 hydrogens bonded to it. The neighbor here has no hydrogens. This neighbor has 2. So the 2 plus 1 equals 3. So that chemical shift must be a triplet, which means we can eliminate A because that says doublet. So therefore, we can determine that 119.8 is the correct chemical shift of the sp2 hybridized carbon in the C13 NMR. So in doing these structure elucidation problems, you really have to look at all of the data and make sure that it's being self-consistent in how you analyze it and connect the pieces. In the next 5 questions here, we're given 4 different structures that are drugs to use to treat ADHD. So question 11 says, which structure will have 10 signals in the C13 NMR between 140 and 120? So that is the aromatic region. And let's just go through A, B, C, and D. So A is going to have 1, 2, 3, 4 in that region. B, 1, 2, 3, 4. C, 1, 2, 3, 4. So the answer must be D. 1, 2, 3, 4, 5, 6. So now that has 6 because there's no symmetry that makes those carbons equal. So we have 6 there, then we have 1, 2, 3, 4, 4 there. That gives you your 10. And again, this has 4 due to the plane of symmetry, which I'll draw in green here. Question 12, which structure will have an odd parent, M to Z, and an intense sharp signal in the IR 1750 reciprocal centimeters? So odd mass. So we have 1 nitrogen that's in the running, 1 nitrogen that's in the running, 2 nitrogens, so it can't be that one, 1 nitrogen. So we're between A, B, and D just based off the odd mass. But then the second clue is 1750. That's telling us there's a carbonyl. So which has a carbonyl? A does, B does not, D does not. So the answer here is A. You have a single nitrogen, odd mass. You have an ester, so that gets you your carbonyl. Which structure will have 2 singlets in the proton NMR that integrate to 3 hydrogens each? That means 3 hydrogens each. You have a methyl group, and it's saying this answer here over underneath should be D. So it's saying 3 hydrogens that are singlets, and so that means no neighbors. And so we have A has a methyl group, no neighbors, but that's 1 singlet. B has a methyl group, but it has a neighbor, so that's going to be a doublet. C is in contention. There's 1 methyl group, 2 methyl groups, but they each have 1 neighbor, so that's going to be 2 doublets. And so D is the correct answer because you have methyl, methyl. There's no neighbors. There's a neighbor here, but typically those hydrogens bonded to oxygen or nitrogen will not split the same way that neighboring CHs do. So those CH3 groups have no neighbors. There's 2 of them, so they're going to be singlets. 14, what structure will have the 1H NMR data shown? So we have 1, 2, 3, 4, 5, 6 unique sets. So we have 3, 2, 1, 2, 2, and 3. So there's, since we have 6 unique sets, we report 6 numbers in the ratio, and then let's add them. 3 plus 2 is 5, plus 1 is 6, 7, 8, 9, 10, 11, 12, 13. So there's 13 hydrogens. And because that number is odd, we can eliminate C, because that has 2 nitrogens, meaning it must have an even number of hydrogens. So A, B, and D, because they all have an odd number of nitrogens, they must have an odd number of hydrogens. So we can do just initially a count of the hydrogens, see if we can eliminate anything that way, and then we can dig into the multiplicity and in the different ratios. So let's go ahead and for A count 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're past that already. 14, 15, 16, 17, 18, 19. So this one's out. We can go to B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is a possibility. We already eliminated C. Let's just go ahead and look at D. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So that's out. So B is going to be the correct answer for this one. And again, we don't even really have to go into these different multiplicities or their integrations or ratios, because we can just eliminate based on the count. And then finally, 15, which structure will have an even parent in the mass spec in an intense sharp signal at less than 1700? That has to be C, because there's 2 nitrogens. The other ones all have 1, 1, and 1, an odd number of nitrogens, so the parent would be odd. The IR being less than 1700 is the amide carbonyl. Our next run of questions is regarding more spectroscopy and additivities in carbon-13 and 1H, and another structure elucidation. So question 16 is asking, what is the chemical shift of the carbon with the asterisks? That is the carbon that's bearing an electronegative fluorine. So you put in those electron pairs, that's delta minus, the carbon's delta plus. And so that one looks the least like methane. So methane CH4, meaning you've done the most substitutions of it. Carbon, 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 and then fluorine. So it should be pushed furthest away from 0, and that would be 98. So that's A. So the one here looks the most like methane because you've only substituted a carbon, so it should be closest to the 0, so that's going to be D, 8 ppm. And now for 18 and 19, you're given a chemical shift of the proton, and you're asked to figure out where those hydrogens would be. So if you look at the asterisks, this molecule only has three unique sets that have a ratio of 6 to 3 to 2. So A and B are the same thing. You're just identifying different methyls of that set with 6. So you can't have that as the response. So you're between C and D. And so if you look at the choices between C and D, C looks more different than methane than D does. So this chemical shift must be 1.88. And then this chemical shift looks most like methane, so 0.81. And looking at question 20, the IR data that we're given, we see the 1500 mark, 16, 17. So you have a signal above 1700. So right away, so we're going to say greater than 1700. We can eliminate the amide because that's going to be less than 1700 for the carbonyl. So all of these have a carbonyl. Now we're just looking at what functional groups they are. This is a ketone. This is an ester. And this is an aldehyde. So esters typically occur a little bit higher than ketones in that region between 17 and 1800, so about 1750. Ketones, 1700, 1725, aldehydes 1700. But we still can't really eliminate anything just yet. If we scan, though, this region here, region 1, there is this signal here that looks different, and that does indicate to us the aldehyde sp2 carbon H stretch, so specifically that bond. So there's two possibilities with that. There's here and here between C and D, but we want to use this other data really to rule out the ketone versus the ester to really confirm that it is an aldehyde. So if we look at the carbon, we jump around here, 1, 2, 3, 3 unique carbons. B should have 1, 2, 3, 4. C will have 1, 2, 3. D will have 1, 2, 3. What does the proton tell us? We have 1, 2, 3 unique sets. So again, what about the proton? In each of those, maybe we'll change the color here to blue. So 1, 2, 3, that'll have 3 unique sets. 1, 2, 3. 1, 2, 3. So we can probably at this point eliminate B, the ketone, based on the carbon being 4. The other ones both have the uniqueness set of 3 and 3. So let's look at some of the chemical shifts, see if they confirm or reject anything. The 9.8 as a triplet, that's typically the only thing that does occur there is the chemical shift of that aldehyde. And again, that gets us between C and D. The difference there is this has 2 oxygens, that has 1. So, if we look at the mass spec data, 58. So 58. Let's build. Let's sort of just subtract out 16 because we know that there's 1 oxygen from the carbonyl. So when we do that, we get 242. And if we take 42 and divide by 12, that's going to give us 3 carbons. So 42 minus 36, it's going to give us 6 hydrogens. So that works out. So C3H6O for this one. And I think what we'll see is that second contribution, so the 2 oxygens, that gives you 32. But if your parent is 58 minus 32, that gets us what? 26. 26 for the remaining C plus H, and what we can see there is that's definitely not going to be enough because we're showing 1, 2, 3 carbons, and that would be 36 total mass units. So that one has to be D, which matches all of the data. The next run of questions here deals with, again, with spectroscopy, some NMR concepts. 21 says, given a C5H10 isomer, which will have a signal with a coupling constant of 15 hertz. So that molecular formula has 1 degree of unsaturation, and what you're seeing in the choices A, B, C, and D is that the degree of unsaturation is an alkene. And really what you're looking for, because that's one of the largest coupling constants, is a trans relationship between H's across the double bond. So A is geminal, B is tri-substituted, D is di-trans, or C is di-trans, D is di-cis. So this has to be the winner because that's the trans relationship, and that has the largest coupling of 15 hertz. So the cis relationship here, that's going to be lower, about 12, 13 hertz. So 22, in consideration of HA in cocaine, what should its multiplicity be like? So your first approximation, it's a unique set, so it's a singlet. You look at the neighbors, you have 1 neighbor there, and then the next you have 2 and 3. So 3 plus 1 gives you 4. However, the angular relationships of HA to those different hydrogens is different. The other thing to recognize is that the neighbors are in different chemical environments, so therefore they are going to have different couplings to that HA. So we can eliminate the quartet, again, because those neighbors are not 3 of the same neighbors, they're different. And actually, we can eliminate the triplet just based on a count. So really, depending on how you analyze it, B or C could be correct. C is a little bit better description because you have an equatorial here, then you have an equatorial here, and then an axial here. So if you have 3 different neighbors, and again, so they're different. So if the neighbor is 1, 1 plus 1 equals a doublet, and you do that 3 times, you get a doublet of doublets. So if you're sort of not aware of the angular relationship, and you just say, okay, this neighbor's 1, that's a doublet, and then this neighbor here is 2, that's a triplet, you could get a double of triplets as well. That's a little less, it's a lesser answer again because the angular relationships amongst those three neighbors is all different. So for 23, the correct answer is C because you do have three different neighbors. However, I did give partial credit of I think, A as a response as well for this. So you're going to have a large coupling because of the trans-diaxial relationship, and then you're going to have two smaller ones because you have these cis relationships that are essentially gauche relationships. So they're going to reduce the magnitude of the coupling. But they're still going to be different, again, because they're equatorial on different neighbors. 24, what functional group will have a sharp, intense signal in region 2 from 2400 to 2200? And it says A signal, so A meaning 1 in the 130 to 110 region, so that's going to be your nitrile. Again, the double bond you're not going to see in region 2. The triple bond is in region 2, but this says A signal. Now when we go to 25, this is going to be B because now we see 1, 2 signals. That's going to be your triple bond in the carbon NMR. So again, pay attention to the wording and use the supplementary information for the spec data that's given to you in the back of the exam. Now the next set of questions is the structure elucidation, and we're going to pull out the relevant pieces of data to put the fragments together. Again, the way the software works here, I can't flip back and forth between the pages and record in a logical manner, so I'm going to sort of front load some of the things from the other pieces of data that I know and write them on the slides as I go. So this is an IR spectrum. The main thing we're looking at, really we want to examine region 3 first, from 1600, 17, 1800 here, region 2, or region 3. And again, that's our typically carbonyl region. We do see a carbonyl intense signal there. If we draw a line down, you'll see that signal hits at less than 1700 reciprocal centimeters. So we can go ahead and assume that the carbonyl is going to be part of an amide. And that is because the amide has resonance. And so that's the only one that's less than 1700. So there's 3 atoms, C and O, that we can use to help us. Again, these are heteroatoms. They contribute a mass of 14 plus 16, so 30 mass units to the parent. Anything else, region 2, we don't see anything. This region 1, this really doesn't look like our normal sort of alcohol or carboxylic acid. We don't really see that pattern. So we're going to move forward in saying it's an amide of some sort. Now we're here to the mass spectrum. We're scanning all the way to the right. We see this higher cluster of masses over here. So the parent is in there. The parent is going to be this signal right here. And if we trace that line down, we see this one's at 100, that one's at 99. So odd equals odd number of nitrogens, and we already saw from the IR data there is at least one nitrogen, so that's odd. So, we can take 99 minus 14. That's going to give us 85. We know that there is an oxygen in there. That's the N contribution, a single oxygen contribution. So we subtract that out. That's going to give us all of the C plus the H's. Now if we take 69, divide that by 12, we can see that 69 times 5 is 60. So 5 seems the most appropriate. If you go to 6, you're up to 60, and then 6 times 2 is 12. So you're past 69. You're at 72. That leaves you no hydrogens. So 5 is the better response because that is 69 minus 60. Again, that's the carbon contribution. That leaves you 9 hydrogens. And so we do need an odd number of hydrogens if we have an odd number of nitrogens. So 5, this is telling us there's 5 carbons. And we already know 1 belongs to the amide. So we have 4 more to deal with. So right now what we're at is C5H9NO in terms of a working molecular formula. Now let's go to the other NMR data to see if that confirms the things we're seeing here from the mass spec. Here's the proton. If we count, this is 1 set, 2 sets, 3 sets, 4. So we have 4 unique sets. And the total of them must equal 9 hydrogens. So you're not given the integrations here. You have to sort of infer things based on what you see. So this is a triplet, this is a singlet, this is a triplet, this is 1, 2, 3, 4, 5. So this is a pentet. So if we see a triplet, that means this signal must have 2 neighbors. So we're talking about its neighbors. So its neighbor must be that. This singlet, no neighbors. Again, that's not telling us what that signal integrates to. It's just telling us about the neighbors. Again, another triplet. And then we have this thing, a pentet, so that must have 5 minus 1. That must have 4 neighbors. But again, it doesn't tell us how many that integrates to. But at least of the 9, we have a start. So 9 minus 2 is 7 minus 2 gets us 5, which means the singlet in the pentet must integrate to the 5. And so again, how do you split that? Is there some sort of symmetry? We need to really look at the carbon data and see what that is telling us. So let's go ahead and do that. We count here 1, 2, 3, 4, 5 unique carbons. This is solvent. You do not count it. We have this signal here. That is due to the sp2 hybridized carbon of the amide. Then you have 1, 2, 3, 4. So 1 sp2, 4, sp3. So we saw from the proton data there was 4 unique sets with a total integration of 9. So what we want to do now is, we still need to figure out what those other 2 sets were, because we know that one was CH2, the other was CH2. Now what does this next piece of data tell us? This is a DEPT spectrum where CH and CH3 are up. So if we count 1, 2, 3, 4, the signal here is not showing up because it does not have attached hydrogens. And of the 4, 1 is up, 3 are down. We already knew that 2 of them were. So now we know the third one. So 1, 2, 3 are down. Those are CH2 groups. When we add that together, 2, 4, 6, we know we have a total of 9 hydrogens minus 6. That gets us 3. So the one that is up must be CH3. That must be the singlet that we saw with no neighbors. Because we have CH2, CH2, so there was a triplet, then you had this other CH2, that's the pentent one, because it must have 4 neighbors. So when we're putting all this together, we have C5H9NO. What should this be? Theoretically, C5. 2 times 5 is 10 plus 2 is 12. We're given C5. A nitrogen is going to subtract. So instead of 9, we have 8. So H4, a degree of unsaturation, is H2. So that gives us 2 degrees of unsaturation. We know that one of them is in the amide. So whereas the other one, it must be in a ring. And so we have these points of attachment is where we have to start filling in the other carbons. So if we look here, we've already written 1, 2, 3, 4 carbons, so we need a 5th. And if we put one here, that would be the 5th carbon. Then we form this last bond. We can see, does this make sense? CH3, CH2, CH2, CH2. There's an amide. We meet the C5H9NO. And so we can say, based on the multiplicities, CH2, this has 2 neighbors, that should be a triplet. This one has 2 plus 2, that should be the pentet. This one has 2 neighbors, that should be a triplet. This has no neighbors, that should be a singlet. That gets you your 4 unique sets, 3 to 2 to 2 to 2, total of 9 hydrogens. It matches the DEPT data. So that would be our proposal. We can use these final questions to help us answer it. So a bit of a correction on the correct responses over in this column here. 26, we know from the mass spec, there's a nitrogen, so we eliminate oxygen O2, Br, ClO, so we have NO. What functional group is present in the IR? Again, that's the amide. We eliminate that because that stretch should be 1800. We didn't see anything in region 2, so we eliminate that. And we know from 26 we don't have 2 oxygens, so we eliminate the ester. So we're dealing with the amide. We said there were 5 unique carbons through the counting. We said the ratio in the proton was 4 unique sets with 3 to 2 to 2 to 2. And then our proposal of the correct structure was this molecule, which is N-methylpyrrolidinone.